For decades, the mysterious behavior of certain materials known as the pseudogap state has puzzled quantum physicists. This phenomenon, tied to the promise of superconductivity and revolutionary technologies like superfast floating trains, has eluded complete understanding until now. A team of scientists has finally cracked the code behind the quantum pseudogap, a breakthrough that may unlock the potential for practical, room-temperature superconductors, and with it, the door to technologies once thought of as science fiction is now closer to becoming reality. Let's begin with what a pseudogap actually is. In certain materials like cuprates, also known as copper oxides, something peculiar happens when they're cooled to extremely low temperatures, below -140 degrees Celsius. They become superconductors, materials that can carry electrical currents with zero resistance, but at slightly higher temperatures, these materials behave oddly. They enter what's called the pseudogap state. Electrons start pairing up as if they're getting ready to become superconductors, but they don't quite make it. Instead, they form a strange intermediate state. The challenge of understanding this state lies in the realm of quantum mechanics. In the pseudogap, the behavior of electrons is driven by quantum entanglement, meaning each electron is connected to others across the material. This creates an immensely complex system that's been impossible to fully model until now. Enter the Hubbard model, a mathematical framework that helps describe how electrons move and interact within these materials. Imagine the material as a chessboard, where the electrons are the pieces. These electrons have either an up or down spin, and they interact with one another in a way that creates an energy cost. The real challenge, simulating this electron behavior, is a monumental task, even for the most powerful supercomputers. To solve this puzzle, the researchers turned to a groundbreaking computational technique known as the Diagrammatic Monte Carlo algorithm. This algorithm allows scientists to simulate the interactions of an infinite number of particles, helping them model the pseudogap state more accurately than ever before. It was this powerful tool that allowed researchers to uncover the secrets of the pseudogap. So, what did they find? As the material in the pseudogap cools toward absolute zero, the electrons organize themselves into rows of matching spins, separated by empty spaces, forming patterns called stripes. Even more surprising was the discovery of checkerboard patches within the electron arrangement. These patches trigger the material's transition into the pseudogap state. This marks the first time scientists have definitively mapped out the structure of this mysterious phase. These discoveries could pave the way for one of the holy grails of physics, room temperature superconductors. Right now, superconductors need to be cooled to extremely low temperatures, which makes them impractical for everyday use. But with room temperature superconductors, the possibilities are staggering. Lossless power transmission that could revolutionize the energy grid, faster MRI machines, and perhaps most exciting of all, superfast levitating trains that can travel at incredible speeds with almost no friction. This breakthrough could even help us better understand quantum gas simulation, an emerging field that explores the behaviors of gases in extreme quantum conditions. This is not only key for theoretical physics, but also for technologies like quantum computing, quantum sensors, and artificial intelligence. The impact of this research could ripple across many fields, but there's more work to be done. While this discovery brings us closer than ever to understanding the pseudogap, questions remain about how it behaves at even lower temperatures. Scientists believe that controlled experiments will provide further answers and help refine our understanding of this elusive quantum state. The cracking of the pseudogap puzzle represents a major leap in quantum physics, with profound implications for our future. From energy and transportation to medicine and beyond, this discovery could help us harness the power of superconductivity in ways that once seemed impossible. Stay tuned, because this could be the key to unlocking technologies that transform the world as we know it. Subscribe for more updates on global innovations and clean energy transitions.